Okay, so let's continue our discussion. And in today's lecture, we'll look at the concept of two-port networks. And so the idea is that, if you want to do interesting things, then you have to connect more number of components, and then the circuit or the system becomes complex. And we need techniques to cope with complexity. And one of the ways in which we do that, in which we simplify the representation of a system, is through a concept called abstraction. So abstraction is nothing but, in our context, is a simplified representation that has the right level of detail for the problem being addressed. So which means that you have a system and you don't need to look at the system in its full complexity all the time. Depending on the problem that you are looking at, you can simplify the system, and that would help in analysis, and it would help in design, and also help you in gaining insight into how the overall system works. So for example, we've been using this particular concept. So we have a circuit like this, and say our interest is in current flowing in the 1 ohm resistor, then all these rest of the elements that you see here, they are not directly important for us. We can take the whole circuit and represent it in the form of a Thevenin's equivalent with the VT and RT. And of course, VT will depend on the voltage sources and current sources here, and RT would depend on the resistors here. But it's a simplified representation and would help us in analyzing the circuit, and also understanding what the role of different elements may be. How, for example, RT may depend on these various elements that you see over here. And if our interest is not in 1 ohm, but let's say 1 ohm and 4 ohm resistor together, then we could, take this part of the circuit and transform it into again a Thevenin's equivalent like this here. So obviously this circuit, the circuit that you see here, or this circuit here, is much less complex as compared to the original circuit here. And if we had more number of components, if we had 100 components and we had just reduced it to, let's say, 3 components here, there's a drastic reduction in complexity, and so it would help us then in determining, let's say, what the current is, and answering many questions where our interest is in this 1 ohm resistor or in this 1 ohm in parallel with 4 ohm resistor here. If our interest is in these two, the rest of the circuit from these 2 points of view can be represented by these ones here. So that helps us simplify things. And we have seen, for example, advantages of it. Remember the power transfer theorem, we had derived it for a very simple case. And we said that we could apply to more complicated cases also through the technique that we just described. If we had a more complex circuit, the maximum power dissipated in RL could be determined using the same concept that we had derived for a simple circuit here. So it allows us to reuse results derived with simple things here. And this was also an example here. So in an RC circuit, we derived this particular result. And if you have a more complicated circuit, well, that can also be transformed using a Thevenin's equivalent into an RC kind of a thing with a different VT and a different RT. And the same result that we had derived for a simple case can be applied here as well. So it allows us to reuse results derived for simple circuits and apply to more complicated circuits. All right, but Thevenin's and Norton's and theorems are not sufficient to cope with the complexity. As an example, let's say I have a circuit like this, and I'm not interested in just in this current here, but I'm interested in both, let's say, on this side and this side also. And therefore, what I would like to do is, this is a simple case, I would like to represent this in a different form. I'm not directly interested in what is here, 2 amperes or 4 ampere or 6 ohms here. My interest is in this 1 ohm resistor here and this supply here. How much, let's say, current is being drawn here. And for example, there's a question that we may want to ask is for a given amount of current, what voltages and all that I need to apply. So the idea is that, we need to build a simplified representation, just like we built in Norton's or Thevenin's equivalent. We need to build a simplified representation for portions of circuit which consist of more than one port. So this is one side of the circuit here, one port here, and then this is another side of the circuit here, another port here. So more than one port is present here, and we'll look at specifically a two-port circuit here. So there are cases where you may want to build a simplified representation of a part of the circuit, and not just between one pair of terminals here, but two pair of terminals, one here and one here, and it could be 3 and 4 in a more general case here. How is it useful? Well, first of all, it would simplify things. If I take let's say there were 10-20 components within this particular part here, and I could represent it by a simplified representation consisting of few components, my overall circuit would become simple, and analysis would become simple, design would become simple from that perspective here. Also, you'll just see, for example, let's say you would recognize that this is a transistor, and suppose I want to analyze a circuit consisting of this transistor, an R and an L and RB and all that here. Now, to analyze circuits, we have seen earlier, you apply KCL and KVL, but you need models. So for resistors, of course, we have Ohm's law. So we need a model for the transistor. And so what we can do is, note that we can take a transistor, and transistor has 3 terminals here, one here, and one here. So what if we could take the transistor and represent it in terms of circuit elements, right? Some kind of a model here consisting of dependent sources and resistors and capacitors. Then we could take the transistor out, substitute it here, and thereby analyze the circuit. We'll see how, what kind of a representation a transistor may have towards the end of the lecture here. Similarly, for example, if we have an amplifier here, so amplifier again, look at it has 3 terminals here, and a pair of input terminals and a pair of output terminals. In this case, there's a common terminal here, so it's a 3-terminal device here. And again, if we want to use an amplifier in a circuit, we need a model of the amplifier. And note that model of the amplifier, so the amplifier cannot just be represented in terms of a Thevenin's and Norton's, because we are talking about 2 pairs of terminals here, one pair here and one pair here. So we need a representation of this thing in terms of 2 pairs, one pair of terminals here, one pair of terminals here, maybe an input pair of terminals here, and an output pair of terminals here. So if we could do that, then of course, we could take the amplifier out, substitute the representation of the amplifier, and solve the circuit, right? Okay, so which brings us to this particular concept of two-port network. That what we are looking for is a piece of circuit here, and there are a pair of terminals here, which we are calling it as, let's say, the input terminals, and a pair of terminals here, which we are calling as the output terminal here, right? So in general, the definition of input and output can also change. So we have two pairs of terminals here, and that's where we call it two-port. One port is over here, and another port is over here. So a port is nothing but a pair of terminals through which a signal can enter or leave the network here. And so we define a voltage across this pair of terminals, V1. The current we define, the convention is current entering is taken as I1. Similarly, we define V2 here and I2 here. And of course, the current I1 goes here and leaves here, and the current I2 leaves here. So the model that we are going to build, the concept that we're going to build, is based on that this two-port network will be a linear network consisting of only linear elements, resistors, capacitors, inductors, and dependent sources. And we'll put a further constraint that there are no independent sources within the network here. No independent sources, or no charge stored on the capacitor, no stored energy inside the capacitor. So with these two constraints, what we'll claim will not rigorously go into justifying it, but it will be sort of obvious to you that we can have a very simplified. So note that a simplified representation of this network. Note that this network can be quite complex. It can have 10 resistors, 100 capacitors, many inductors, many dependent sources. But what we'll say is that you can replace all of that, just like we did it in Thevenin's and Norton's equivalent. You can replace all of that in terms of a simplified representation. And the simplified representation will have only 4 elements. So no matter how complicated these things are, it can be represented in terms of 4 elements. So let's see how we can do that. And so coming back to this example, we said, okay, so we can take the transistor out, and we said you can represent it in this particular form here. Okay, so this we'll see when we'll actually deal with transistors. So you can represent it in the form of a resistor here, a dependent current source, and another resistor here. So in this case 3, because transistor is a specific device which we call as unilateral, in the sense that the input affects the output, but the output does not affect the input here. So that's where there is no effect of output on the input side of the terminal here. On the input pair of terminals here, base and emitter are the input pair of terminals, collector and emitter are the output pair of terminals. So it's a 2-port network being represented by 3 elements here. So okay, so let's go forward. Similarly, amplifiers also, we could represent it in this particular form here. This amplifier that you see here could be represented by a resistor here, which we call as input resistance, a dependent voltage source, and another resistor here, which we call as an output resistance here. So this is also an example of 2-port network with one terminal which is common to both the input and the output ports here, and we can represent it in this particular form here, a transistor here. So let's and note that the amplifier here can be quite complex. So amplifier here that you can see here is 1, 2, 3, 4, 5, and current sources and resistors and all of that. So it's quite complicated, but we can represent this amplifier in terms of these 3 elements. And so it would be interesting, and one would like to ask, how do I determine these 3 elements, Rn1, AV0, and R01? How do I determine? And once we have this representation, then wherever this amplifier is present, for example, in a circuit like this, we could take the amplifier out, substitute it by this representation, and thereby analyze the circuit and predict the properties of the circuit that is there. So there are different ways in which we can represent this 2-port network. One of them is what we call as in terms of Z parameters or impedance parameters here. So in this case, we take I1 and I2 as 2 independent variables, and we express the remaining 2 variables in terms of I1 and I2. So we write V1 is Z11 I1 plus Z12 I2, and we write V2 is Z21 I1 plus Z22 I2 here. So if I1 and I2 are 2 independent variables, now V1 would obviously, because it's a linear network, so V1 would depend linearly on I1. So that's where V1 is linearly dependent on I1. And V1 will also depend on I2 in general. So Z12 times I2 here. So Z11, because we have 1 here and current is also I1 here. So that's why Z11 here. And similarly, the current is I2 and the voltage is V1 here. So that's where we have Z12 here. And we can represent them in a matrix form: V1, V2, Z1, Z11, Z12, Z21, Z22. So what we are saying is this 2-port network can be represented by these 2 equations, which are sort of obvious from the fact that we are taking them as a linear network. And if I1 and I2 are 2 independent variables, then V1 would depend on in this particular manner here. Now these 2 equations can be represented in a circuit form. So V11, Z11 I1, we can represent it by a impedance here, and Z12 I2, we have to represent it by a dependent voltage source here. Note that each term is a voltage term because the left hand side is a voltage here, and it depends on I2, so that's why it is a current, this is a dependent source, so here. And similarly, V2 is Z21 I1 plus Z22 I2. So that also can be represented as, this term can be represented as simply an impedance here. And this one can be represented as current dependent voltage source here. So both of them are current dependent voltage sources here. So what we are saying is any 2-port network that is given to you, and it's a linear network with no independent sources inside, and you could represent them in this particular form here. 4 elements: Z11, Z12, Z21, and Z22. Okay, so of course you can determine, if you're given this whole network that is here, you could analyze it and determine what the values of Z11, Z22, and Z12 and Z21 are. But you can also experimentally measure it. Okay, And how do we do it? So both, whether you want to analyze it or experimentally measure it, how do we do it? So let's say you want to determine Z11. So what we can do is we can note that our two independent variables are I1 and I2. So if I put I2 equal to 0, meaning open circuit here, and I apply a current source here, I1, and then you measure the V1 and V2, and so Z11 will be V1 by I1 because I2 is 0 here, and also Z21 will be, you measure the open circuit voltage here, V2 by I1, and you will get Z21 here. And in the next case, you put I1 equal to 0, open circuit the input, apply a voltage here, apply a current here, I2, and do the same thing here. Z22 will be V2 by I2, and Z12 is V1 by I2. So note that what you can do is, given any circuit here, you could open these terminals here, open circuit it, apply a voltage here, then use KCL, KVL, whatever technique that we've already done, analyze it, take these ratios and determine it. Experimentally, what you could do is same thing, open circuit it here, apply a voltage here, experimentally measure V1 here, experimentally measure V2 here, and therefore you have Z11 and Z21. So note that any piece of unknown circuit, complicated circuit, any amplifier that is given to you, even if you don't know what is inside it, you could take that piece of circuit and experimentally you could do this. You could open it out here, apply a current source, measure V1 on the oscilloscope or a multimeter, measure these, and thereby simply take the ratios of the experimentally measured values, and you have Z11, Z21, and similarly you have Z22 and Z12. So any circuit, any unknown circuit, any unknown device, a transistor or something else that is there, suppose somebody has invented a new transistor, and a model for it has not been built yet, but you could take that particular transistor and experimentally measure Z11, Z21, Z22, Z12, and thereby you have a representation of the transistor. And then you have a representation of the transistor, and that representation you could deploy anywhere in your circuit and determine what the circuit performance is going to be here. All right, so we have names for it. So Z11 is called input impedance. So we said this is an input port and this is an output port here. So V1 by I1 is the input impedance here with the output open circuit here. So open circuit input impedance. Z22 is from this side here is V2 by I2 with input open circuit. So we call open circuit output impedance here. And then we have transfer impedance, which is Z12 and Z21 here. All right, so let's look at it as an example here. So let's say we have this RC network here, and we would like to represent it in the form of Z representation here, Z parameters here. So in this case, I'm taking, of course, as I said, you can analyze the circuit and determine Z11, Z12, and Z21 and all that. But here I'm taking more like an experimental approach. So let's say what we do is, or a simulation approach. So we keep the output open circuit. We keep it open circuit here, and we apply voltage here. And note that Z11 is V1 by I1 with I2 equal to 0. So these are my output terminals here. I2 is 0 because I've kept it open circuit. And we've applied a voltage. We could have applied a current source and measure the voltage. So both of them are equivalent. V1 by I1. And in simulation, so I'm simulating it, so I have all the values here. So the phasor value is 1 angle 0. The current that is flowing here is showing 32.117 with an angle of minus 140. But note that I1 is going into the circuit here. So that's where we add a minus there, and the minus you can transform it into an angle plus 180 kind of a thing here. So anyway, so we can determine V1 by I1. From simulation, of course, you'll get these values, and you can determine what Z11 is. Experimentally, we would have done the same thing. We would have applied a voltage here, and we would have measured what is using an ammeter, measured what the current was. Okay, and next semester when you look at it in the lab, you can measure what the voltage is, and you can look at the current flowing through it, current flowing through it is nothing but same thing as voltage across this particular R1. You can observe it on the oscilloscope, and you can see what is the phase, and all of those things you can determine. Similarly, we can determine what is Z21. Z21 is V2 by I1 with I2 equal to 0. So with this thing open circuit here, we measure the voltage here. So the voltage is given 485.57 millivolt with an angle here. The current we had already seen, the current which is flowing in here, and therefore in a similar manner we can determine Z21. For determining the remaining two parameters, we open circuit the input terminal here, and we apply, let's say, a current source or a voltage source here at this particular point here, and we do the same thing. In this case, we have all the values that are there here, so we determine Z22 and we determine Z12 here. Okay. So in summary, then what we are saying is this piece of circuit that you see here, we can represent it in the form of 4 elements: Z11, Z12, Z21, Z22, 2 impedances and 2 current dependent voltage sources here, and these are the values here. Z11 is here, Z22 here, Z12 and Z21 here. And note that for this particular circuit, Z12 is nothing but same as Z21 here. And circuits like that, in general, if you don't have any dependent source in a piece of circuit, you will always find that Z21 is equal to Z12 here. And such networks are called reciprocal networks. So we have a 2-port network, and reciprocal in the sense that you'll see, suppose I apply a voltage here at the input, and I short the output terminals, and let's say I measure a current I. And it is reciprocal in the sense that now if I exchange the configuration, if I apply voltage at the output here, and I short the input, I will measure the same current here. Right? So it's reciprocal. You apply a voltage here, you will measure a current which is I here. Now if you apply a voltage here, you will measure the same current I over here, and we call such networks as reciprocal networks here. And look at it here. We are applying a voltage here, 1 angle 0, and shorted the output here. And so the current flowing here is 21.38 with the angle of 160. Now let's exchange the two. Let's short the input and let's apply the voltage here. So we apply it here and we short the input. And if you measure the current, same phasor here, you'll find the current as 21.38 angle 160 here, phase of 160 here. So these are reciprocal networks here. You apply a voltage and you get certain current. You apply a voltage on this side, you'll get the same current on this particular side here. Okay, and we said that these are reciprocal networks, and one characteristic is they will not have any dependent. So we're not justifying it. There's no, we're not giving you a proof for it. But dependent sources, if there are dependent sources, then the circuit will not be reciprocal. Let me give you an example. So we have, this is the input port and this is the output port here. So we've shorted the output port and applied a voltage at the input port. And if I apply 1 volt, let's say I calculate current. So if this calculation is correct, let's say this is minus 0.5 amperes here. Now we short the input, we apply the voltage here, same voltage 1 volt. Well, I'll measure current of minus 0.1 ampere here. Because, you know, in my 2-port network, there are dependent sources here. The circuit is no longer reciprocal here. Okay. So Z12 is, the important thing is that for reciprocal networks, Z12 is Z21. And therefore, we don't have to determine 4 elements. We just have to determine Z11, Z12, and Z22. And only 3 elements are independent here. Now, Z parameters are not the only way you can determine or represent the 2-port network. You could take, for example, V1 as independent variable and V2 as independent variable. And the dependent variable I1 and I2 you could express in terms of V1 and V2. So I1 is Y11 V1 plus Y12 V2. I2 is Y21 V1 plus Y22 V2 here. So that's an alternative representation. And in a matrix form, it can be represented in this manner here. And in a circuit form, it can be represented in this way here. So note that I1 is Y11 V1. So we are talking about current being sum of 2 components here. That's why it shows up as a parallel network here. Current divides into 2 parts here. The first part is Y11 V1 here. So it's a impedance or an admittance here. The second part is a voltage dependent current source here. So it's I1 is Y12 V2 here. So V2 is on the other side here. And so the only way we can represent this particular current here is in the form of a dependent current source here. So voltage dependent current source here. Similarly, if we look at I2, so I2, if we look at the second term Y22 V2, we can represent it by a simple impedance or an admittance here. The second part depends on V1, and we don't have any V1 in this particular part, so we have to represent it in the form of a dependent current source here. So voltage dependent current source Y21 V1 here. So we can also represent our two-port network in terms of these Y parameters here. Y11, Y12, Y21 and Y22 here. Okay. And as usual, we can determine now, if you want to determine Y11, well, then you put V2 equal to 0. You short the output and then you take these ratios here. And similarly, once you put V2 equal to 0, if you look at the second equation, if V2 is 0, so I2 by V1 will give you Y21. Next case, you short the input side here, V1 equal to 0 here, apply an output V2 here, and then you'll get I1 by V2 and I2 by V2. So you can determine all of these things there. And similarly, they have their names. Y11 we'll call it, because it's the ratio of current and voltage. We call it admittance, because we are seeing it on the input side. We call it input admittance here. And because it's being determined with output short circuited, V2 is 0, so that's why we call it short circuit input impedance, input admittance here. Similarly, Y22 we call it short circuit output admittance here. So it's the ratio of output current versus output voltage here. That's why we call it output admittance here, with the input short circuited here. So that's why we call it this one here. And the remaining two are transfer admittances, the ratio of current on one side, voltage on the other side. So these are transfer admittances here. All right, so Y parameter is another representation of the two-port network. And now I'm sure you can think of other ways of doing it also. For example, we could choose I1 as an independent variable on this side and V2 as an independent variable, and thereby express V1 in terms of I1 and V2 and I2 in terms of I1 and V2 here. So I2 in terms of, so we call them hybrid parameters because we have mixed up independent variables are current and voltage. In the previous cases, the independent variables were either both currents in case of Z parameters or both voltages in case of Y parameters. In this case now, we have mixed the two, and so these are called hybrid parameters here. H11, I1, H12, V2 and all that. And in a matrix form again, they can be represented in this way. And in a circuit form, we are writing V1 as sum of two components here. So voltage being sum of two voltage drops. So this is represented as a series circuit, H11. So V1 is H11 I1 here. So it's basically a impedance here. And this one is we have to represent it as a voltage dependent voltage source here. And I2 is being represented as sum of two components. So it's a parallel network here. Parallel network, the H22 V2 is fine. And this part we have to represent it as a current dependent current source here. So H21 I1 is a current component, and it depends on I1 current flowing here. So that's where we represent it in this particular form. So these are hybrid parameters. The importance of hybrid parameters are that these are commonly used to represent transistors. And we can think of the inverse hybrid parameters, also called G parameters here, where we take V1 as an independent variable and I2 as an independent variable, and we can write it in this particular form here. So I1 and V2 are dependent. This is in a matrix form, and by now we know we can represent it in this particular format here. Okay. So there are other ways of representing also, but we'll confine ourselves to these four representations: Z parameters, Y parameters, H parameters, hybrid parameters, and the inverse hybrid parameters are called G parameters. Okay, and so we mentioned something about reciprocal networks, and I said that only Z11, Z12, and Z22 there are only three independent variables here. So we can use this particular fact to obtain a further simplified representation for reciprocal network. So note that I can write this V1 as Z11 minus Z12 I1 plus Z12 I1 plus I2. And similarly, we can write it in this particular form. And the reason why we are doing it is that this is the conventional Z parameter representation of a two-port network. But if we look at these two equations here, we can represent it in this format here. Z11 minus Z12 is this element here, and Z12 I1 plus I2 here. So we put Z12 here, I1 comes from here, I2 comes from here. And similarly, V2 is Z22 minus Z12 here. So we can represent it in this form of this looks like a T here. This is here and this is here. So we can represent it in the form of a T network. And the importance of this T network is that for a reciprocal network, we need only 3 elements. Here, there were 4 elements here. And there was a dependent source here and a dependent source here. And in this case, note that these are all impedances here. Z11 minus Z12, Z12 here, Z22 minus. So without any dependent sources, we can represent this, have this representation here. Okay? A simplified representation. With simple algebraic manipulation, we can write it, but only for a reciprocal network. Y parameters also, we could do the same thing. We can do Y1 plus Y12, we can rewrite it in this particular form. And this is a general form, but we can represent it in this form here. Y11 plus Y12, note the first term. And the second term is Y12, V2 minus V1 here. So we write it in this form here. And the Y22 plus Y12 is simple here. And I2 is minus Y12, V2 minus V1 here. Okay, so we write it in this particular way here. So this is what we call as a pi network here. This looks like a here, here, and here. So it looks like a pi here. So if you have a Y representation and it's a reciprocal network, we can use this form here, but this requires 4 elements and has dependent sources. This one, we could simply represent it in terms of 3 admittances here, 1, 2, and 3. Now, of course, for the same circuit, we are saying you can determine Z parameters, Y parameter representation, H parameter, or G parameter. So all of them must be related together because it's for the same two-port network. So, and it's easy to see that if we have a Z parameter representation here, let's say you have already done a Z parameter representation and you've analyzed the circuit, determined Z11, Z12, Z21, and Z22. Well, it's easy to manipulate this and write it in this form here. You know, you can express I1 in terms of these parameters here. You could take these two equations and cast it in this form, and therefore you could obtain Y11 in terms of Z parameters, Y12 in terms of Z parameters, Y22 also in terms of Z parameters here. So we'll leave the algebraic manipulation. We'll not spend time on it, but you can verify that I1 by taking this equation here, these two, we can write I1 as in this form here, express it in terms of V1 and V2, and I2 also we can express it in terms of V1 and V2, where delta Z is Z11, Z22 minus Z12, Z21 here. And therefore, what we are saying is, if you have obtained Z parameters, well, Y parameters you can obtain through these relationships. Y11 is Z22 by this delta here, and similarly there are other relationships. And of course, vice versa also I can do. Suppose you have taken a circuit, experimentally measured or analyzed and determined Y11 and all these Y parameters that are there. And for some reason you are interested in Z parameters, well, you can obtain Z parameters also, right? And of course you can then, you know, it would be obvious that you can determine the H parameters and the G parameters also from the one single set of measurements here. A few more things and then we'll wind up our discussion. Suppose there's a two-port network, you've already analyzed it, and you have the Z parameter measurements for that. You've already done that. And there's another network B, and let's say you've measured or analyzed it, you have these Z parameters for these two networks. And now let's say, so you've done that. Now let's say you make a more complicated network and you combine them together. You combine them in series by series here. So this one is added up like this. You can see a series connection here at the input and series connection at the output here. Well, it's easy, and I'll leave it for you to show that, easy to show that now for this bigger network, this is the input port V1 and I1 and V2 and I2. You can show that the Z parameter for the overall network is a sum of Z parameter of A plus Z parameter of B. This is a matrix addition here, so which meaning that Z11 is Z11A plus Z11B. All right, so a simple algebra will convince you that Z parameter is sum of these two Z parameters. Similarly, we could take same network A. Let's say we've determined Y parameter representation here, and we network B and we've done a Y parameter representation here, and we connect them in parallel. Note that this end is connected here, this end to a common here, this end is connected here, and this here, common here, and similarly on the output side here. So we've connected them in parallel, right? This end is connected to this end is connected to this end here. So that's how you connect things in parallel. And it's easy to show that for the composite network, the Y parameter would be the sum of Y parameter of A plus sum of the Y parameter of B. Y11A plus Y11B. Okay, so if you're combining networks, these are helpful results that you don't have to analyze determine the Y parameter for the whole network again. These are simply sum of the Y parameters of A and B here. Okay, so we said as an example, we were talking about a transistor, and let's say this is some transistor circuit, and you have to analyze, you're trying to use a transistor in a circuit and do something interesting with it, and you want to know what will be the output voltage versus Vs. So we said that, of course, then to analyze this particular circuit, to predict what will happen, you would need a electrical model of the transistor, because without the model, then we cannot write our KCL. We can write KCL and KVL, but we cannot proceed. We won't be able to obtain the full equations, and therefore we won't be able to analyze it. But now, so let's say this is an unknown entity. So what you could do is, you could take this particular transistor and let's say experimentally take this particular transistor, experimentally measure the H parameter representation. H11, H12, H21 and H22. So experimentally what do? We apply voltages and currents, and we measure output voltages or output currents, and through that we determine the parameters as ratios of voltages and currents. We've already seen how to do that. So let's say you take the transistor, you don't know anything about the transistor, right? What is inside it, what its properties are and all that. But you could take the transistor, experimentally measure its H parameters. And now what you do is, and these are the H parameter representation. So now what you do is take the transistor out, it's a two-port network, and substitute this particular model here. Note that H12 is 0 here in this case. And so you represent it in this form here. So it's not a reciprocal network. H12 is not same as H21. In fact, we call it as a unilateral network here. The input affects the output, but the output doesn't affect the input. Note that on the input side, because H12 is 0, so there's no effect of the output on the input side of the circuit here. Okay, and so what you do is you take the transistor out, replace it by this representation here. So H11 is 1 kilo ohm, so you represent it here. H21 is a dependent current source here. So H21 we have already determined 100, so 100 times I1, and H22 is 10 minus 5 admittance here. So admittance is nothing but inverse of impedance, so it's 100k here. So we can take the transistor out, represent it in this H parameter representation, and now we have a circuit that we can easily analyze and calculate what the effect of transistor in this particular circuit is. So without knowing anything about what is inside the transistor, or it could be any other thing, you could measure its H parameters and thereby analyze the circuit. Okay. And for example, now we could predict that if you have a circuit like this, then V0 by Vs, you could build an amplifier with a gain of minus 50. And if you wanted a gain of 100, well, you could then manipulate 10k here, 1k here, 1k here, and all of those things, and see how you can obtain a gain of 100 here. So an interesting question does arise is which parameter to use. Should I use a Z or a Y and an H or a G? And the answer to such questions is it depends on the application and the nature of the system. So we'll briefly look at it here on the side of the nature of the system here. Okay, so let's say there is a system here, and when you look at it from the output side here, it looks very much like a, the nature of the system is such that it looks like a dependent current source here. It's more like from the output side, it's like a current source. And current sources, note that ideal current sources will have very high impedances in parallel to them. So let's say the nature of the system is such that it looks like a dependent current source. Okay, so it's natural to model it as a dependent current source. So now, if you try to take this network and you are not aware of, let's say, that from the output side is closer to a current source, and you try to model it using a Z or G parameters here, it can be problematic. For example, if I try to model it as Z parameter here. Now Z parameters, note that Z parameters you determine by making, let's say, Z11 is V1 by I1, and you will make I2 equal to 0. Now I2 equal to 0, so what you will be doing is you'll be applying, let's say, some voltage at the input. Let's say 1 volt you apply to the input. You'll open circuit the output here, and you'll measure the current here, and you'll take the ratio V1 by I1. It will give you Z11, right? And similarly the other parameter here, okay? Because you've made I2 equal to 0 here. All right, so if we apply V1 equal to 1 volt, note that what you've done is I2 is equal to 0. So I2 is 0 here. So in this case, I2 is open circuit. V1 is 1 volt. So this is 0.1 ampere current. And 0.1 ampere current would flow through a 10 to the power 6 ohm and will develop 10 to the power 5 volt. Which is obviously impossible. This system will break down 10 to the power 5. So what it is saying is, that you cannot open circuit the output terminal here. If you open circuit the output terminal, in this case, a very high voltage will try to develop, and the system may get damaged here. So then the representation of this circuit or measurement of Z11 will be problematic, because to measure Z11 you will have to do this kind of an experiment. You'll have to apply V1 here with output V2 open circuit. You'll have to apply some reasonable value of V1. If you're thinking, well, you may apply 0.1 volt here. Even then you'll have 10 to the power 4 volt here. Okay, so you'll have problems. You won't have a reasonable voltage at the output here. Okay, so that will create an issue here. Similarly, G parameter will also cause the same thing here, because it requires output to be open circuited here. So I2 equal to 0 here, and the moment you put I2 equal to 0 here, again the same thing will happen here. So both Z parameters and G parameters are then not suitable, because you will have difficulty measuring them. You will not, experimentally you would have problems in determining it. Okay. On the other hand, then for us, both the Y parameters, Y parameter would be easy to determine in this case, because note that it requires, Y parameter will require not to output to be open circuited, but output to be short circuited here. So V2 is 0 here. Okay, so determine Y11 and Y21, you would want V2 to be 0 here, and V2 equal to 0 is no problem here. So if you short it, what would happen is the current here would then obviously flow here, and the current would be reasonable. So for example, if you were trying to determine Y11, it would be I1 by V1, V2 equal to 0 here. So let's say you apply V1 as 1 volt or something like that, and then so the current is 0.1 ampere here, which will flow through this part here. You can put an ammeter here and measure it. So there's no issue with it. Okay. So determination of Y parameters requires V2 and not I2 to be made 0, and thus causes no problems. And same is true for H parameters. So if we have a situation like this, that when you look at a circuit and from the output side it looks more like a current source, then the Y parameters or the H parameters make sense. The Z parameters and the G parameters then are not a good representation of the system here. So our choice reduces to this. Now, for the sake of discussion, suppose this two-port network is such that when you look at it from the input side, it looks more like a voltage, an ideal dependent voltage source here of this kind here. Like if you think that a voltage source in the sense that the resistance in series with the voltage source is very, very small here. So ideal voltage source will have zero resistance or impedance here. So suppose from looking from this side, it looks more of this kind here. Now, so our choice is already between these two. So now from the input side, if it looks like this, so let's see which one, if you try to determine Y parameters here. So Y parameters here, to determine Y12 or Y22, you will have to short the input voltage here. So you have this kind of a circuit here. So you'll be applying, let's say, Y12. So you'll apply, let's say, V2 equal to 1 volt. And input is shorted here. And you would try to measure I1. So input is shorted here. V1 is 0. And you're applied, let's say, 1 volt here. So this is 10 volt here. Now we have a problem. 10 volt divided by 0.1. 10 volt divided by 0.1 would be 100 amperes here. So that will cause a problem here. So excessive amount of current would flow. So whenever you take a voltage source and you try to short it out, obviously you'll have problems. So then determination of Y12 and Y22 is the problem here. So what it is pointing out is that Y is not a good representation for it. And you can easily verify then that H representation would be a suitable one here. So what we are trying to say is that the nature of the system, some systems you can represent them by either Y, H, Z or whatever. Perhaps it doesn't really matter. But in some case, the nature of the system is such that when you look at it from the output side is more like a current source. When you look at it from the input side is more like a voltage source here. And therefore, an H representation may be closer to the nature of the system and may be more appropriate. And if you're trying to experimentally measure the parameter values, you will have no difficulty. On the other hand, if you're trying to apply a wrong model, then you may get into problems with experimental measurements. Okay. All right. So as a summary, what we are trying to say is that when you have a piece of circuit with two ports, with a pair of two terminals here, and it's a linear circuit and doesn't have any independent voltage or current sources within it, well, you can represent them in these four. There are more numbers of two-port representations, but these are four common ones: Z parameters, Y parameters, H parameters, and G parameters here. Okay. All right, so let's stop here.